So now we need to talk about dissociation constants. So dissociation constants give us an understanding of the strength of acids and bases, and basically the extent to which the acid or base has dissociated in solution. So for this learning outcome, we need to be able to recognize that the strength of acids is explained by the degree of ionization at equilibrium in aqueous solution, and this can be represented with chemical equations and with equilibrium constants, so Ka. Then we also need to be able to determine the expression for the dissociation constant for weak acids, so that being Ka, and weak bases, Kb, from balanced chemical equations. And so this is using a formula which we have for Ka and Kb, which is similar to the one which we use for equilibrium as well. And then we need to be able to analyze experimental data to determine and compare the relative strengths of acids and bases. And then we need to be able to use appropriate mathematical representation to solve problems, including calculating dissociation constants, so that being Ka and Kb, and the concentration of reactants and products. So in order to calculate Ka, we have this reaction constant value equation which we use, and so we can see that it pertains to the reactions down the bottom. So Ka is going to equal the conjugate base times the conjugate acid divided by the original acid. So essentially it's both of our products divided by our reactant. And so in this reaction, we've got, for example, if we've got Ha dissociates into H plus and A minus, we would then say that Ka is going to equal H3O plus times A minus over Ha. And so this is going to be where Ka is going to be the dissociation constant for the given acid. Ha will be the acid before dissociation. H3O plus or H plus, depending on whether it's a weak acid or a weak base, will be the hydrogen ions or protons. And A minus will be the conjugate base. And so it's important to note that with our two reactions, we can either have a dissociation that proceeds for a strong acid where we've got Ha dissociates into H plus and A minus, or we have the concept where it dissociates in water, so Ha plus H2O dissociates to form H3O plus and A minus, and so that would be a weak acid. And it's also important to note that when we look at our Ka value, we can see that it's got H3O plus, A minus, and Ha, but we haven't got the H2O in there. And that's because with a weak acid, we have what we know as a heterogeneous system. So we can see with our strong acid, we have a homogeneous system because all of the reactants and products are in the same state, so they're all aqueous. Whereas with our weak acid, we've got some in the aqueous and some in the liquid state. And so this means that the one in the liquid state is not included because water is not considered to be part of the reaction in terms of how it's acting. So although it accepts a proton, it's not considered to be part of the equilibrium constant, as it won't affect the constant. So we hence only consider the aqueous components of the weak acid when we make the dissociation constant equation. Then the same goes for Kb. So with Kb, we can start off with our strong base, our strong base would be BOH, and that can dissociate into B plus and OH minus. And then we can have our weak base, where we've got B, which is our base, added to water, and then that B accepts a hydrogen ion from the water to become BH plus, and then the hydrogen ion from the water, when it's been lost, we're left over with OH minus. And so that's for a weak base. And so we can see that that's then been applied to our KB, where we've got BH plus times OH minus. So that's our conjugate acid times by our conjugate base divided by B, so that being divided by the base. And so that would be our acid dissociation constant, where Kb is a dissociation constant for the base, B is the base before dissociation, BH plus or B plus is the conjugate acid, and OH minus is the proton the proton absorber, or our conjugate base, which is left behind. And so it's also important to note that, remember that we didn't include H2O in this when we did our Kb value, because it's not considered to be part of the acid base dissociation, and it's not considered to be something that affects the Kb value. Now finally, we need to look at pKa as well in order to understand this. And so we can actually use pKa, which is the inverse of of Ka, in order to find pH. So we can do pH equals pKa plus log in base 10 of the concentration of conjugated base divided by the concentration of conjugated acid. And so this is known as the Henderson-Hasselbalch approximation, and it can only be used for weak acids and weak bases. So for example, we could have pH equals pKa plus log in base 10 of A minus divided by HA, and that would be for a weak acid. Whereas we can have pH equals pKa plus log in base 10 of B divided by BH plus, which would be for a weak base. And so the reason why we can't use these for a strong acid or a strong base is because it's relying on the fact that we have a reversible reaction. And so with a strong acid or strong base, we assume full extent of dissociation, so we assume that it's not a reversible reaction. So pKa, we can say, is the inverse of Ka, so we can say pKa is going to equal negative log of Ka.